issues recently. How do I look at my sound? Connect some overlays. Well, anyway, I'm going to assume that you can hear me. So what's the problem? I've been trying to get better at explaining neurosymbolic AI. So I'm actually planning for the next few days to kind of do a bit of a review. So at AI, there was this neurosymbolic AI panel. I think I'll look at that today, but there's lots of on YouTube as well. And so the issue is that I work with neural nets, and I work with symbolic AI, and I work with them in concert. But I think that whenever I hear other people talking about it, they just seem to come at it from a different angle. So one of the things that I'm hoping to do in the near term is just to get a better idea of what other people mean, and when they talk about this, when they explain it, what are they looking to explain? So let's get to that. Let's see here. Great. All right, well, let's just start with this simple explainer. 1 minute long.
Today's AI systems provide us useful recommendations and predictions, but their accuracy depends on lots of annotated data to train neural networks for every new task. To address this, IBM Research is championing a new approach called Neurosymbolic AI. It combines the statistical, data-driven learning capabilities of neural networks with symbolic reasoning techniques. For example, a neurosymbolic system could use a neural network's pattern recognition capabilities to identify objects in videos or images, then rely on symbolic AI programs that apply logic and semantic reasoning to identify relationships among these objects. The MIT-IBM Neurosymbolic Concept Learner learns by simply looking at images and reading paired questions and answers. The goal is to create explainable AI systems that can tackle more complex tasks while increasing accuracy, learning from fewer examples, and using less data.
Yeah, so nothing really surprising there. All right, well, let's just jump to this panel. What the heck?
Thanks so much for inviting me. This is a great class and a great program, and I'm really.
All right, refresh that. There we go.
Welcome, everyone. My name is Christian Kessing. I'm super happy to have such a great set of panelists here. So welcome to the Neurosymbolic AI panel. We have Marta, Leslie, He, Louis, and Matthew. And I would like to take the opportunity to first set the stage for the panel, and then afterwards, each of the panelists will introduce her own viewpoint on this question. What is neurosymbolic? Why do we need neurosymbolic? Do we need actually neurosymbolic AI? So what is this about? We are living in super interesting times. And if you compare the beginning of AI and what is currently happening, then you have maybe two opposing, sometimes it feels like opposing views on that. Namely, on the one hand, that the argument is AI system should really be able to deal with symbols. And then other opinions saying, maybe we don't really need symbolic systems here. So you can view that in very different ways, but one way is that on the one hand, we have deep neural systems, or generally maybe talking about differentiable AI. And on the other hand, we have a lot of interesting stuff in symbolic AI, going into logic, but also maybe formulating scientific theories in terms of crisp formulas. We have planning, we have background knowledge, we have constraints. And so you could ask, do we have to combine that? Maybe, maybe not. You may also simply ask this very deep scientific question of how can we actually combine discrete and continuous information, learn about them, and also do reasoning about them? Now, you hear a lot about that in the news, but also, of course, in all the great publications at AAAI, but also at many other venues. But I would also like to remind all of us that there has been done already quite a lot. And I guess, and I apologize for that, I'm missing a lot of work here as well. So we have, on the one hand, a lot on neurosymbolic approaches. We also have already a lot about how to combine, for example, probabilities and statistical information. And there are other books coming soon out as well. However, this is not just about AI. It's also about understanding thoughts and cognition in general. So definitely what we are trying to touch upon here is also very much related to the twin science of AI, cognitive science, because it's really exciting to understand this question: how do we humans get so much from so little? But also, of course, from neuroscience. And I think this is all a little bit triggered within the AI community by this general theme idea of thinking fast and slow by Daniel Kahneman. But let's be a little bit more specific. So I think we need something like a combination of learning and reasoning, because with reasoning, by having general rules and world knowledge, we may much easier understand that a village speed limit of 230 is maybe not really realistic, and maybe we got tricked, and we would like to override what we observe. But also for practical reasons, you may just be interested in combining different AI and computational methods in order to speed up well-known, more symbolic methods to, well, make maybe neural or differentiable approaches more trustworthy. So there's also this interesting question of just how to combine the different AI algorithms. But you may...
Okay, so we got two use cases here. One is the Kahneman approach of having like a kind of system one, system two dichotomy, and the other is computational reasons.
I also argue that at least in the way we communicate with the machine or the machine with us, we may want to use some symbolic information, right? And this might be based on logic, but you may also see it as natural language, but you may want to have an underlying formal language. So here, for example, we are showing that you can have confounders that are quite tricky to correct if you just look at visual inputs. But if you also extract and try to build up a symbolic system, of course, in a close interaction, in close interaction of the different systems, then actually you can revise the system by even providing negative feedback, saying never use something in specific, so you deal with negation. So I think overall, this is all very much driven by what is called by now the third wave of AI, where we say data is impressive, but data is not everything. And we need AI system that can acquire human-like communication and reasoning capabilities with the ability to recognize new situation and adapt to them. So overall, and to be also a little bit provocative here.
Wait, let me hear that again.
Is neurosymbolic and try to build up a symbolic system, of course, in a close interaction, in close interaction of the different systems, then actually you can revise the system by even providing negative feedback, saying never use something in specific, so you deal with negation.
All right, so that wasn't a very clear explanation. Something about building a system and then you have the ability to provide negative feedback. But I thought, machine learning has a lot of negative feedback and we have negative examples. Never do something maybe. There was talking about some, at least interactions between humans and machines should be in symbolic form. What we got here? So, don't know what XIL is. There's a large cube and a small cylinder. And then we have some pictures that mean nothing. And then we have, or mean something to somebody, probably not, nobody who has read this paper. Visual explanations are often insufficient. Got some authors here. I think those are the authors. And then looks like we got some kind of CNN. Reasoning module slot. Okay. Yeah. Okay. So missing this point of the argument. I guess we don't have a very good articulation, but let's see where we go.
So I think overall, this is all very much driven by what is called by now the third wave of AI, where we say data is impressive, but data is not everything. And we need AI system that can acquire human-like communication.
Right. All right. So we're now, see, this is the argument we make often in causal inference, which is, it's not an opinion. And as it feels like the neurosymbolic people often make this an opinion, like data is nice, but it's not, we need more to do stuff, but we need human intuition and all. But that feels like you're making some kind of value judgment. But what we really want is, well, the fact rather is that no, there are some queries that we simply cannot rely on data alone for. I mean, mathematically speaking, that's a fact. Not without some kind of inductive bias that you're going to have to code in yourself. You're not going to get it from the architecture of some algorithm.
And reasoning capabilities with the ability to recognize new situation and adapt to them. Right. So overall, and to be also a little bit provocative here, is neurosymbolic AI maybe the new Big Bang in AI? Should we really somehow say this is the big question, namely understanding how we can combine differentiable approaches and symbolic approaches? So I guess this is what we would like to discuss in the panel here. And we will start with Louis Lamb, and then we will continue with Matthew. So having more the differentiable as well as the neurosymbolic view maybe on this question. Then going over to Marta, where Marta will tell us a lot about, I guess, model checking. I mean, Marta invented a lot on PRISM, probabilistic, symbolic model checking. Then going over to he, telling us about combinations of probabilities and logic, and also deep networks, how they can help us there. And finally, arriving as Leslie. And I guess Leslie will us all remind, is that really new neurosymbolic? Isn't that just what we have done anyhow in our research, and we should just enjoy and go ahead with our research? Yeah, the idea is that each of them is providing her view in, let's say, 7 minutes, maybe 10 minutes, but also leaving space already questions that are targeted to the opinion. But then in the end, we would like to also go into the discussion and also take your questions from the audience.
This is an hour and a half.
With that, I will stop and hand over to Luis to present his view here.
Can I speed this up? Oh, shit.
But do you think that... With that, I will stop and hand over to Luis to present his view here.
Thank you. I'm going to share the screen. Just waiting for the authorization. Okay. Okay. I hope you can see this presentation. And I also like to stress that when I look at the painting, I saw a small wave under it over here. So I thought, well, Christian was quite right in terms of thinking about the waves, about the duality, maybe the particle wave duality in physics and so on. And we are living in this era now that Christian highlighted, that we are perhaps confronting a new way of expressing AI concepts and AI foundations so that we can build more trustworthy, explainable, interpretable AI systems, as it's our aim. And this is joint work with Arthur Garces. As Christian said, we've been working on it for a long time. And we hope we can keep the same high standards of last year in the AI debates, even though they are virtual debates this year. But last year we had some luminaries from deep learning, luminaries from the AI community, and even a Nobel Prize winner that was also mentioned by Christian Kirsten here about thinking fast and slow. And since then, there has been a lot of attention in AI. And I will try to give you some glimpses of what happened over the last few decades in this field called neurosymbolic AI. And I hope that by the end, Leslie can say that neurosymbolic AI is worth pursuing, is not something that we have to not to consider for the future of science. And there was a spark, there was a beginning of interest in neurosymbolic AI since, let's say, the transition from 19 to 20 before the pandemic. There was this great AI debate where Yosha Benjo and Gary Marcus discussed about the role of hybrid models in AI. Also the fireside conversation with Daniel Kahneman, where Daniel Kahneman emphasized the role of systems 1 and 2 from cognitive psychology and decision-making in AI. And so several analogies have been drawn between AI systems 1 and 2 and Kahneman's and Tversky's systems 1 and 2 from psychology and cognitive science, as Christian mentioned. Moving forward, by the end of 2020, we also had a new AI debate number 2, where several influential researchers in AI, cognitive science, neuroscience, as Christian highlighted.
That's me. on stage of a bunch of Turing Award and Nobel Prize winners because I'm a boss.
Which is quite important for the future of AI too, in terms of building more realistic models that correspond or have a biological correspondence. They were discussed. But also we highlighted the limitations that we have at the moment in AI systems that are pretty much directed to interpretation, to explainability, to trust. And in order to do that, we need a symbolic approach integrated with a neural approach. And we see that because in a way that AI is very impressive, by showing us tools, techniques, and technologies that quite impress even the mainstream media. When we think in terms of science, it's always good that we also think about the foundations. And as Christian mentioned, there has been a group of people over the last decades that have been thinking about and building the foundations of this field. And these, of course, include the neurosymbolic guys, including the people who work on relational learning, or Star AI, as Christian is one of the pioneers, as also Leslie and others here. And we think that this is the way forward for science. We can think in terms of showing that science works, or the field of AI works in practice, but we need solid foundations. And this has been the objective of many, many people researching AI over the last decades. Another important thing that we have to mention here is one needs to cater for very important properties and very important characteristics that AI systems have to show so that we can build trust in users, trust in the ones that will deploy AI technologies across several industries. And when one thinks in terms of interpretability, in terms of verification, I'm sure that Marta will talk about it, in terms of fairness, in terms of...
Let's actually read through this. So machine learning is a vibrant field of research with a range of exciting areas for further development across different methods and applications. There is a collection of specific research questions where progress would directly address potential public concerns about machine learning or constraints on its wider use. Interpretability: can we create ML systems where the reasons for popular decisions and recommendations can be understood and interrogated? How do you get this to go away? Anyway, that's annoying.
Causality, even in terms of security, all of this.
Privacy, what are the technical somethings used in new ways? Fairness and dealing with real-world data. How can real-world data be curated in usable forms, addressing real-world messiness, systematic or social bias? And great causality. How can machine learning methods discover cause and effect relationships? Human-machine interaction. How do we design learning systems so that they can work with humans safely and effectively in security? So this, I imagine this is more of like an interpretation. Like if I have a bot, this is more, or maybe this is related to interpretability. Like the learning agent has to communicate with me. There has to be some kind of interaction with me as the agent, but it's got to be using language that I understand because I can't speak whatever it is happening inside a neural net. Security, how do we ensure? So this is pretty. I mean, this feels almost like a list of things that we know are kind of that deep learning doesn't do, at least the canonical version of deep learning doesn't do all that well at, right? Like, for example, adversarial attacks on neural nets. But I don't know, defining this as the goals of this new wave of Neurosymbolic AI seems meh. Oh look, there's actually the power and premise of computers that can learn by example. Yeah, this feels like you're defining a new wave of capability in terms of the problems of the previous of the state of the art. But what you want to do is really be imaginary about so like, for example, causality. I don't want to just discover cause-effect relationships. I want to build an agent that can reason causally. I talk, ideas like blame and intention and regret. I don't mean like bandit algorithm regret. I mean like I shouldn't have married this woman. I'm actually very happily married. I counterfactual regret. That's a powerful reasoning algorithm. We should be more explicit about that.
These properties and these features are very well responded and tackled with symbolic techniques in terms of, for instance, when one thinks in terms of computational foundations of AI or the foundations of computer science. And in terms of what we aim at doing is exactly what Christian said. He showed the example about the speed of a car. But here we show that this small girl here, it happens to be my daughter, when she's trying to learn to do something, she gathers information from an uncertain environment and builds a way of formalizing her reasoning to repeat the learning process. And this is an analogy that quite fits well what we are trying to do in Neurosymbolic AI in terms of relating to real-world experiences and real-world environmental situations where uncertainty is present. However, in order to take a decision by the end of the day, one takes a deterministic decision and deploys his or her cognitive abilities to take an action. And also, one of the key questions that we have to ask here in terms of building more trustworthy and interpretable, explainable AI systems is how to identify the necessary and sufficient building blocks of AI, and how these building blocks, this evolvable, this uncertain world, can lead us to build effective ways, effective tools, and effective technologies that make AI trustworthy. And in order to do that, we need to highlight and we need to search for the best representations for neurosymbolic techniques. And this leads us to what Christian said in his opening statement. It leads us to several challenges for principal integration of learning and reasoning. And this is a school of thought that there are many people who defend. And in order to build these richer AI systems, I go back to the AI debate from Triple AI last year, where Daniel Kahneman was present and corroborated this point. He said that system one, the system that acts fastly, the system that reacts to the environment, certainly has some form of knowledge representing in it. And also, he also stated that system two does involve certain manipulations of symbols, because system two.
Right, so I was at this debate, and this was actually an interesting point. So Kahneman points out that, so like there's this kind of, I guess, according to Kahneman, people interpret his system one, system two metaphor a bit too rigidly. So for example, the idea that maybe, and I'm guilty of this to some extent, I think, like the idea that system one is basically perception, like turning pixels into some kind of representation that can be immediately acted upon. So like the system one is vision, and the falcon sees a mouse and kind of acts on that information, and that higher reasoning things that kind of happen in the frontal lobe are all system two types of things, and language is often kind of shoveled in there because language has to do with semantics and objects that exist in the world that we as agents can interact with, and therefore maybe require some high level reasoning. But Kahneman says that no, I think that system one knows language, but when it comes to kind of manipulation of symbols, that's a system two thing. So that's this a system one and system two almost seems like a Rorschach test for kind of what it is you already work on. But anyway, I think it's useful to in these discussions.
Two is the one that's more.
I mean, actually, one thing that pleases me about it is just the acknowledgement. Like if we're talking to Kahneman, then we're talking about cognitive science, and if we're talking about cognitive science, then it allows us to focus on a very rich body of work by computational cognitive scientists who are essentially trying to reverse engineer human intelligence to achieve artificial intelligence. And there is a lot to of useful things there in terms of building algorithms that the traditional kind of deep learning culture has rejected because they don't like theory-based or model-based methods. They like radically empirical methods. And once you get past that, once you get past radical empiricism and you start to look at some of these methods and see what they can get you in terms of being able to make conclusions that you can't make from data alone, then you can start saying like, okay, well, which of these so-called conclusions that require a theory-based model as well as data are actually really useful. And so for me, for example, I work in the startup space, and one thing that you as a startup, you're going to have, if you're working as a startup in the AI space, you're not going to actually have that much data to begin with. And even if you do, like it's never really enough. Every client is different, or every customer is different, every user, subscriber is different, and so you want to kind of be able to structure that knowledge in some setting. Yeah, but also, frankly, most of the data in the world is small data that's unstructured and could use some human theory, some system 2 level symbolic reasoning to come in and help work with that data.
Reflexive system 2 is more related to logical reasoning, is more related to the symbolic world of AI in the traditional sense. And so these parallels have been made over the last couple of years between AI researchers and cognitive scientists of how to build this integration of learning and symbolic reasoning in the form of some logical reasoning, some form of traditional techniques being integrated with deep learning, which of course has been very successful. And as Christian mentioned, over the last decade, we have shown that it's possible actually to represent, learn, and to use neural learning models to represent rule-based systems and to effectively realize some form of sophisticated reasoning, other classes of reasoning, such as temporal reasoning, epistemic reasoning, and so on. And also this was emphasized in the last debates between, for instance, the one that involved Yosha Benjo and Gary Marcus. And these techniques, this kind of approach that have been used have been extensively described in several papers, in several books, and in other publications that are coming in the near future, as Christian said. So what we aim here and what we are trying to do and trying to build is to build something where logical reasoning or symbolic techniques and well-founded semantics that I'll mention later is something extremely important when one deals with computer science. And the question that Christian asked about dealing with differentiable AI.
What was... I'm trying to figure out what the... Trying to figure out what the actual, I wonder if, hey, so people in the chat right now, can you hear me? That sucks. I think I might have some sound issues. I'm gonna keep going here. See if I can debug them.
With respect or in comparison with symbolic AI is the kind of questions that perhaps Martha can talk about a little bit about it later. Is a question that already in the late 60s was confronted by computer scientists. And the field, for instance, of computer language semantics was grown about and developed about the late 60s, aiming at building a formal semantics for computer science. And since we think in terms of AI here, we also may need to consider this kind of definitions, this kind of strategy in terms of research foundations, so that one can offer a more formal semantics to AI so that we can build more trustworthy systems. The same way applies to computer science. In order to have solid computer science tools that are applied in critical systems, one needs a formal semantics. And this formal semantics typically comes from, let's say, the logical world or the discrete math world and so on. And in order to illustrate what I've been doing here, I illustrate some systems that we call connectionist model logics or connectionist temporal logics, where one considers ensembles of neural networks as representative of a possible world semantics or of a state-based semantics. And in this kind of representation, we're even able to prove some theorems of convergence, and we are able to prove that some sorts of neural networks, depending on the way you build the neural networks and the translation algorithms, are able to compute fixed point semantics of reduced logic programs or model logic programs or some sort of rule-based systems. So in this way, we have revealed some connections between the symbolic world and the deep learning world or the neural learning algorithms that are typically used in AI. It's also important to consider that when one thinks in terms of the evolution of AI systems and evolution and adaptation of systems, it's important to think in terms of the temporal evolution of these systems and the revision that we have from time to time in the ability of these systems to converge to different learning procedures and different approaches. And also, we think that in order to do so, we need a temporal formalization of how this process happens in terms of defining a more adequate semantics. And here I just highlight that some of these papers are not so new. And this particular paper where we define this connectionist temporal logic for deals with epistemic evolution was published exactly in one of the same issues of neurocomputation, where Jeff Hinton published his famous fast algorithms for deep belief nets. Of course, deep learning took over from that era, but we hope that neurosymbolic AI can also benefit from some attention over the next years. So just to finalize this first few minutes, I present some challenges for well-founded neurosymbolic AI. Of course, AI has been extremely successful over the last decade in terms of applications, in terms of dealing with real-world problems, in terms of dealing with real-world data sets. However, from the foundational side, we see that first-order logic and other higher-order knowledge extraction from large networks that can be shown provably sound and explainable can be something that we have to pay some attention here, because this is something that we need in terms to have interpretable systems that we can prove properties about their behavior. Another point that we bring about here to discuss is the role of common sense and efficient combinatorial reasoning. How can one deal with the complex deep networks that are trained on large amounts of multimodal data? This brings us some issues and some problems that we have to tackle in terms of combinatorial reasoning. In the same way, if one wants to program systems or build systems that exhibit goal-directed common sense reasoning, we have to consider, even when one thinks of these large language models, of how to do specifically with the semantics of natural language processing that involves common sense reasoning. And finally, when one considers the applications of AI, of course, human in the loop and human network communications can be part of multi-agent systems that promotes communication, promotes argumentation between multiple agents, argumentations between natural argumentation and artificial large language models. And one has to deal with the protocols between these agents that will communicate, they will ask questions, and they will check his or her understanding. And whether or not an AI system truly understands what it does is another recurring theme that we have to consider in the current debate. And we believe that when one has to deal with this tension between reasoning and learning, we have to consider that this is not a new problem. This is not something that has just appeared in the AI community. We have to consider, for instance, this statement by Les Valiant from Harvard University, Turing Award winner, is that the tension between learning and reasoning has a long history, reaching back at least as far as Aristotle. So this problem that we're dealing here is a foundational problem, is something extremely important for the future of AI, but we have to bear in mind that questions in science may not be answered by the first approach or by the first people who apparently give some of the answers that may satisfy the users of some technology. Thank you, Christian. I might have been a little bit over time, but we'll have time to catch up later. Thank you.
Great, thank you. Yeah, I think also that reasoning and learning has a long tradition, but hopefully we will make more progress now. Maybe Matthew, you can already put up the slides, and while I'm asking Luis, it was interesting for me that you're not putting even more emphasis on software engineering, because I feel if we really want to do software engineering for AI, we need more symbolic stuff.
True. It's true. The question about more emphasis on software engineering, I was expecting that Marta would answer it, but I will answer it. There have been applications of combinations of model checking and machine learning. We've showed some cases in the papers from about 8 years ago. And if one needs to define systems that are trustful, for instance, in critical applications, the norm in computer science to have verifiable systems. At the moment, we do not have verifiable in the same way that we have in software engineering, Christian. We do not have in AI systems verifiable systems. And in this way, we combine deep learning systems with some form of temporal formalism, some kind of verification formalism is a challenge, something extremely important for the future of AI in terms of being used as a day-to-day software engineering tool. And from this answer, I might think that Marta will catch up from that because she's been working on verification for a long time. But this is a school of thought that I firmly adhere to. I think that, for instance, in terms of model checking, one can combine model checking with machine learning and using, for instance, counterexamples provided by model checking tools as ways of refining the model and specifications and improving the quality of the model and the quality of the systems that you have at hand when you work with formal specifications and formal verification of critical systems.
Okay, so I mean, let's look forward also to Marta, but Matthew, I think now it's your turn.
Yeah, I don't have any slides.
Neuroscience can tell us.
Yeah, so first, I just want to say how delighted I am to be joining this panel. This is really fun and exciting. I guess my role by default would be to represent the kind of differentiable, fully differentiable or neural network approach, and also the cognitive science, neuroscience perspective, which I'm very happy to do. I thought I'd start though with maybe some more general comments, and there's something about this topic that makes everybody take a historical perspective, which is just obviously no coincidence. But when I sat down to put together my notes for these opening comments, I found myself thinking about my experience in grad school in the late 1990s, studying cognitive science at CMU, and my experience was the computationally oriented people in my department were organized into two really clear camps. On the one side of the hall were the connectionists, and on the other side of the hall were the symbol processing people, including Herb Simon. There definitely were a few people around back then who were arguing for a hybrid approach, but I think most people in the two camps felt like their favorite architectures would ultimately prevail. Still, at the same time, looking back, it's also clear that both sides did have nagging doubts. The connectionists worried, I think, about whether neural networks would ever show sufficiently structured information processing, and the symbol processing people, whether they'd be able to figure out a way to get learning to work or a way to handle just the inherent messiness of the real world. Of course, in the years between then and now, it's been a very interesting tug of war for about a decade. It seemed like symbolic methods, especially once they were given a probabilistic dimension, would smother out the competing neural approach. And then, of course, neural nets came roaring back. Admittedly, that started with applications that were less interesting to symbolically minded people. But recently, and especially with large-scale language models, I think it's fair to say that culturally, the burden of proof feels like it's shifted to the shoulders of the symbol processing approach. However, having said all of that, I have to say that even though I was weaned in this world of two competing camps, my own personal preference is not to start with a position on representations or architectures or algorithms, but instead to start by defining the kinds of behavior we're trying to capture. And I think the kinds of behavior that lead to discussions of neural versus symbolic strategies or how we can integrate these generally involve what I tend to call revealed inference. In other words, behavior that gives evidence that an agent has made some structured, usually inductive inference about the data that it's processed in order to generate new responses. In the most interesting cases, behavior shows program-like structure, either in its own form or in the inferences that you can see underlie it. So the question, as I see it, is what kind of system do we need in order to get this kind of revealed inference in behavior? Sounds like so far everybody's kind of going to be on the same page there. In considering the alternatives, I think a lot of people would agree that it's important to take into account a major innovation in neural network design, which started to gain traction a few years ago and which is now more and more canonical, which involves building neural networks that operate on exchangeable vectors. This started with slot-based episodic memory architectures like memory nets and the differentiable neural computer, and then was followed by graph nets and most recently transformers. Operating on exchangeable vectors immediately endows neural nets with a computational substrate that ordinary recurrent neural networks would be very unlikely to induce through learning. It makes more or less native things like discretization of data, variable binding, relational representation, things that have traditionally
AI community. We have agents, argumentations between, we'll ask questions. Consider that this is by the first people who apparently give some of the answers that may satisfy the use specifications and formal verification of critical systems.
Okay, so let's
instance counterexample
about my experience in grad school in the late 1990s studying cognitive science at CMU, and my experience was the computationally oriented people in my department were organized into two really clear camps. On the one side of the hall were the connectionists, and on the other side of the hall were the symbol processing people, including Herb Simon. There definitely were a few people around back then who were arguing for a hybrid approach, but I think most people in the two camps felt like their favorite architectures would ultimately prevail. Still, at the same time, looking back, it's also clear that both sides did have nagging doubts. The connectionists worried, I think, about whether neural networks would ever show sufficiently structured information processing, and the symbol processing people, whether they'd be able to figure out a way to get learning to work or a way to handle just the inherent messiness of the real world. Of course, in the years between then and now, it's been a very interesting tug of war for about a decade. It seemed like symbolic methods, especially once they were given a probabilistic dimension, would smother out the competing neural approach. And then, of course, neural nets came roaring back. Admittedly, that started with applications that were less interesting to symbolically minded people. But recently, and especially with large-scale language models, I think it's fair to say that culturally, the burden of proof feels like it's shifted to the shoulders of the symbol processing approach. However, having said all of that, I have to say that even though I was weaned in this world of two competing camps, my own personal preference is not to start with a position on representations or architectures or algorithms, but instead to start by defining the kinds of behavior we're trying to capture. And I think the kinds of behavior that lead to discussions of neural versus symbolic strategies or how we can integrate these generally involve what I tend to call revealed inference. In other words, behavior that gives evidence that an agent has made some structured, usually inductive inference about the data that it's processed in order to generate new responses. In the most interesting cases, behavior shows program-like structure, either in its own form or in the inferences that you can see underlie it.
Right.
So the question, as I see it, is what kind of system do we need
Automatic induction.
in order to get this kind of revealed inference in behavior? Sounds like so far everybody's kind of going to be on the same page there. In considering the alternatives, I think a lot of people would agree that it's important to take into account a major innovation in neural network design, which started to gain traction a few years ago and which is now more and more canonical, which involves building neural networks that operate on exchangeable vectors. This started with slot-based episodic memory architectures like memory nets and the differentiable neural computer, and then was followed by graph nets and most recently transformers.
Really, yeah.
Operating on exchangeable vectors immediately endows neural nets with a computational substrate that ordinary recurrent neural networks would be very unlikely to induce through learning. It makes more or less native things like discretization of data, variable binding, relational representation, things that have traditionally been considered the preserve of symbolic methods. There's obviously no need for me to list the successes of this vector-based approach, especially given the attention that's been deservedly gained by large-scale language models recently. The questions, which obviously many of us are discussing on a daily basis, are whether this kind of approach will allow useful discretization to be learned from high-dimensional data in cases where the input is not already tokenized, as it is in most language applications, and also whether vector-based processing is a strong enough bias to yield all the kinds of structured inference that humans, for example, can make. My own personal recent research experience leaves me, I would say, hopeful, but not completely certain. On the one hand, I've been involved with work that...
So I've seen that exchangeability of vector stuff before. I think it had to do with, graph neural nets and, the challenge of making it such that a representation doesn't... You basically you kind of want certain invariances to be such that the representation is the same regardless of whatever form that's with respect to the invariant property, right? So if it's translation invariance, so sliding something from here to over here, what you really want is that the vector representation of that image should not change based on just that sliding. So this is the first time I'm hearing it as like, this is kind of a breakthrough in neural nets that enables it to be a one step closer to symbolic reasoning.
That shows that transformers can do some pretty fancy forms of visual question answering, including handling counterfactuals in the Cleverer dataset, which was actually on the background of the title slide. Forms of inference or forms of question answering that seemed to some people like they might require classical symbolic scaffolding. On the other hand, my group is about to release an RL task environment that...
There's actually, so like there's a data set of a natural language data set where you have kind of counterfactual answers like counterfactual question answering, and me as a causal guy, a causal modeling background makes me, I'm inclined to think that you would need some kind of structure to handle that, but it looks like transformer networks actually do pretty well at that task.
Requires structure learning and inference in a chemistry-like setup, and we find that otherwise state-of-the-art transformer-based RL agents do very poorly on the structure learning part of the task. And so, perhaps they need something more. Perhaps they need some sort of, symbol processing like infrastructure to get there. One thing that we did find in running RL agents on this chemistry-like task that I mentioned is that it really helps if the agents are given some kind of external symbolic side information, sort of analogous to a written cookbook. And this brings me to one final question that I'd like to put on the table for discussion, which is how far we might be able to get with agents that aren't internally symbolic, but which learn to manipulate external physical symbols, as humans obviously do. And how much of that kind of external activity might then be spontaneously internalized, supporting structured behavior that feels symbolic. Okay, so that's my 2 cents, and I'm really looking forward to discussing all that.
I'm not going to go back. So what was it? Something about external, something that feels externally symbolic and that's internal. Didn't catch that bit, but trying to go backwards here is dangerous. So just keep going.
Thank you, Matt. That is really exciting. If I correctly understood, you are wondering whether we should actually separate the differentiable maybe and the symbolic part to some extent as well. So let's assume we have even two networks that, the internal and the one that I use to maybe communicate with the outer world. Or so it's a little bit like pen and paper we have, right? We have our own brain, and if I start communicating, I start writing on the paper in order to tell the world what I'm thinking, and that doesn't mean that you really understand my brain. I don't even understand my brain, but maybe we can understand what we communicated.
Yeah, right. In other words, this is an alternative to a hybrid architecture, which proposes that a system with a softer set of biases, like this kind of vector-based architecture that I talked about, would then have its internal processes enriched by engaging with essentially external cultural technology, which would then, that activity would sculpt the dynamics of the more general purpose internal machinery in such a way that what results is something that's constrained to be program-like. I think this is not a new idea in cognitive science, as you're intimating, but I think we're now at a point with deep learning technology that we might be able to do some actually interesting experiments with how far it can be pushed.
Yeah, I mean, me personally, I agree. Maybe we can also discuss that then later. But I think what is also interesting and important is that many AI researchers should now start to understand how to set up experiments and how to design them much more than we are used to, right? We are driven by simple benchmarks. And then talking to some of my cognitive science friends, Josh Tenenbaum, Konstantin Rotkopf, you get so impressed how much they think about the experiments. And so I think this is already useful, getting in touch with each other and talking about that.
It's just one comment on that, if I may. Like, there's an inherent tension that's created right now by the growing awareness that you're articulating, that we really need to probe our system's knowledge in order to understand what the nature of that knowledge is. But the strategies that cognitive science give us generally are only applicable in very simple situations, and we simply rely on the human subjects' pre-experimental experience, all the experience they had before they walked in the room, in order to give us interesting behavior. And so I think there's a big problem right now bridging that gap between our ability to analyze the behavior that our agents have and the fact that we're training these agents in very rich circumstances that are hard to analyze. Anyway, something that I'm wrestling with on a daily basis.
Yeah. And I guess we will come back to that. But talking about symbols, maybe we can also think of model checking in a very similar way. But I guess Marta will tell us. Marta, please go ahead.
Hello, thank you also for the opportunity. So I come from the verification community, formal verification community, and like many researchers, I was intrigued by the steady march of machine learning and the successes in particular. And a few years ago, I started applying verification techniques to machine learning in order to provide certification. So what I want to focus on is certification, but I also want to give my perspective on how I see the field of machine learning and AI, and where verification, and in particular theoretical techniques from the semantics community, can contribute. So I will start first by paraphrasing, using an example that Moshe Vardi had in his slides when he was talking about Daniel Kahneman observations. So Moshe Vardi is an international leader in my field in verification, and in particular logic. So he identified machine learning with fast thinking, which is focused on questions like, is this a stop sign? Now logic, on the other hand, is for slow thinking. Do you stop at a stop sign? And he concluded by saying that it's now a grand challenge to combine logic with machine learning. And this is a view that I also subscribe to, but I think that we need to be very smart about combining logic with machine learning. So I fully support we need neurosymbolic, but I also think we have to be very clever about it. And perhaps what Matt was talking about was one way in which we can be clever about it. But here I want to talk about certification. Now, certification provides provable guarantees, and this is the main objective of certification. Now, if I look at Moshe Vardi's description, what we actually need here is deeper answers to a deeper question. So imagine yourself riding in an autonomous car. So there are already two agents. There is me and there is the car. And the question then becomes, can I trust the car to stop safely at a stop sign? Now,
that's a good use case.
Can we actually learn from verification or use verification in order to answer this kind of question? Now, even if you ignore mechanics, this is not simply just a reliability question. I mean, there is software involved. Software can go wrong, and for this you can use logic, you can use verification, but there are also continuous elements. So you probably need control theory, discrete switching as well. There is perception involved. So we do need, neural aspects, because we know perception is actually best in that context. But there is risk estimation, and this is a safety critical system. There is uncertainty. So we need probability, we need statistics. But what we also need is knowledge, including common knowledge. I think that was on Luis's slides. So we need what is known now as good old-fashioned AI, and perhaps also epistemic logics and cognitive reasoning in order to handle the whole situation. So that's what we all need, okay? But where are we right now? If you want to consider provable guarantees for machine learning, then the first question you would be asking is guarantees for what? Okay, so guarantees for what? Is it accuracy? Is it robustness? Is it safety? Is it fairness? ... So for accuracy, accuracy just simply measures the percentage of tests that the system has passed. So this is just testing. I'll come back to that in a minute, just testing. Now, robustness, typically local robustness, will focus on a specific input, and then consider the problem of the neural network's answers robust for that specific input if you allow an adversary, perhaps, or noise to perturb the input. Okay. Now, what we actually do in this case is we fudge the issue, even for something like image analysis, because we don't consider proper similarity measures. What we consider is a proxy, typically LP metrics. So there is already a fudge, in that case. Now, for safety, okay, I've already given you an example. For safety, you have to have a safety assurance framework. For fairness, but which fairness? Okay, but the biggest issue is that all these that I've mentioned have trade-offs and tensions. So if you try to optimize for one, you end up with a Pareto effect that you actually decrease. You are forced to be suboptimal for another. So that was machine learning guarantees for what, but you also have guarantees when. Is it design time? Is it runtime? Is it training time? So all these questions need to be answered. Now, in contrast, my field, logic verification, considers provable guarantees, but they are always with respect to a specification and a model. So there is a clear specification of a property, there is a model, and then the objective is to provide a proof that the model satisfies the specification. And we usually have a proof system. We like to have proof systems that are sound, so that we cannot prove anything that's wrong. Proof systems that are complete, ideally. That's not always true, but ideally you would want to prove anything that is right. And logic and verification, unlike testing, can provide guarantees for all inputs. There could be infinitely many inputs. Now, Dijkstra famously said, testing can only show the presence of errors, not the absence. Only the presence of errors, not the absence. So and people have already considered what would be needed if we were only allowed to test autonomous cars, how much effort would be needed in order to provide even statistical guarantees that the system is 95% safe. It comes down to millions or billions of miles if you actually want to have some confidence guarantees on that. Okay, so this is
cool. So I'm going to stop it there. I'm going to hop back into it about halfway through. Right. So given my virtue of kind of having grown up in probabilistic programming, probabilistic graphical models, causal models, dynamic systems, and using neural networks in all of these settings. I guess that makes me a neurosymbolic AI inheritor by default, but I've hopping on to some of these explainers and panels to figure out how other people are constructing a problem, and it's making sense in ways that is articulating things that, say for example, like when I put on my causal modeling hat, I'm rarely talking about engineering best principles and testing and verification. When I'm talking about probabilistic models, I'm not talking about things like identification given a structure of a model and how to even learn the structure of a model. So it's interesting that neurosymbolic AI feels like it's coalescing on things that I've been kind of worried about from disparate areas for a while. Although that makes me a bit suspicious. It feels like it's just more like a shopping list for things that we wish deep learning could do, but that it can't. So there's that. And there's a lot of interesting things to learn here as well. Maybe in the future kind of reading group, I will grab that Springer book by Lois Lamb and work through that a little bit. But that's all for today. Thank you for watching, and I'm going to this month. I promise to get a bit better about this whole streaming thing, and I'll post a schedule, and I'll even have like fancy graphics and stuff popping around the image, so I'm not constantly outproduced by 16-year-olds. So look forward to diving into some of these topics further going forward. Thank you.